Hi, my name is Lou. I want to talk about a project I did, which is to analyze Facebook data using a Java graph class that I wrote, and also the statistic package R. And I want to share with you what I did and what I have found out. Okay, so I'm going to share my screen. And I want to share the presentation. Okay, so the goal is to find out communities in Facebook data. So what is a community? Now here is a example, a very simple case that I came up with. So you have a person here. Each of the dot is a node. Excuse me. And so this person is connected to 9 other people. And this person is connected to a different 9 other people. And so is here. And these are the key people in each community. They are connected to one another in this type of setting. Okay. I have another example, which this can be seen as a community where these 4 people are connected, and this is a community, and this is. And each of the community are connected by, like these 2 people are connected, and these 2 people are connected. So you will ask, how can you, what's the method to use to find out communities in the Facebook or in the network, in the graph data, like in this example? How do you find out? So what I'm using is I'm using the Driven-Newman betweenness algorithm. Okay, what does that mean, betweenness? So if we take this as a example, so if I see this as a community, as a city, let's say this is a city, and this is a different city, and here's another city. And people within the city have little road to travel, they're connected. And from this city to this city, you have to go through this only one route, which let's say it's a highway. So if I take every person in this graph, let's say this person here and this person here, in order for this person to reach out to this person, he or she will have to travel to, let's say, the shortest path would be to this central person, and from the central person go to another central person in this city, and then you would reach out to the person that you want to connect with. So in the algorithm, I'll take every node and compute the shortest path from this node, from a given node to all the other nodes. And then I will record the shortest path and count the number of times a particular path is used, and which we can see from this example. These highways are going to be highly used, where the road inside the city, in the community, will not be used as much. So with my computation of all the shortest paths and then counting how many times an edge is used, I can then take the top used edge and cut that. Say like I cut this edge. Then, or let's say these 4 edges are all highly used, so I cut all these 4, then you will see the community will form, right? I'll have 4 different communities. In this case, it will be these 2 edges are highly used. I cut those, then I would end up with a community. Okay, so this is what the algorithm said. Okay, so so it does take the shortest path between any 2 points or nodes and use a breadth first search. And then the edge, I'll compute a edge utilization by counting for each of the shortest paths, how many times an edge is used. And then I will get the most used edge, and I will cut that. Then I will use the method that does strongly connected component of a graph to tell me what are the connected components I have left. And if I haven't feel like I cut enough, then I will go back and do step 1, 2, 3, 4 again. Now you can see this method is quite challenging. If you have, let's say, n nodes, then for you to compute the shortest path between any of the n nodes, in the worst case, well, in the case, right, you will not compute, let's say, self to self, but that would just be n cases of this. But if you have, like, you need to compute to all the other. So algorithm-wise, in the big O theory, the computation method, you will do n times n times of the shortest path computation. And each of the shortest paths, you will travel the number of edges in the worst case. So the worst case, it will the big O will be n squared times the number of edge. And you can see this with the increase of n, this times of computation just increase quite quickly. So this problem is actually a pretty hard problem. It's one of the example of an NP-hard problem. So the way to find out the answer is to go on the computation, and if the computation takes so long, light years, then that's not practical. And okay, so that's step number 1 is the hardest thing. As part of the step number 1, when I found a shortest path, and I need to add it to all the edges, that it gets used one more time. Since I'm using a hash map, this actually is pretty good. So it's a big O of 1, means it's a constant time since it's hash. And afterwards, after I get all the shortest paths computed, and each of the edge, how many times it's used, are counted, to find the top edge that's being used, I just need to go through all the edges. So this is not bad. It's just a magnitude of the number of edges being used. And then I would, step number 4 is to use a strongly connected component. And this is not that bad because I'm just going through each of the node. I walk it one way and then I walk back. So step number 4 is not that time consuming. So it's really step number 1, this part of the logic is very time consuming. Okay, so that's one challenge of this problem. Of course, the other challenge is to know when to stop. Like for this case, if I cut all these edges, I end up with a community with 10 nodes. Do I stop here? Do I keep on cutting? So there is no definite answer like here is where you stop. You can cut all the way until you have a single node left. So what I found out is you will go through each time you cut an edge, you will study what you end up and see if it needs to be cut further. So that's much a like trial and error type of way. Okay. So now I'm going to talk about the Java classes that I used. I totally used 3 Java classes. One Java class is the graph class. Now that's the heavy lifting core method, and I call this cap graph. And the reason it's called cap graph is capstone graph. That's part of the project. I'm using that methods. So I have a set of basic methods, which you would add a vertex, you will reply with how many vertices I have in my graph. This method supplies all of the nodes. Okay. I can also test a particular integer, whether it's part of the node. And I can save it in the file. I can add an edge. I can remove an edge. I can, given a particular node, get all of its neighbors. I can transpose the graph, and I can write out the graph on a standard I/O with a toString method. So these are all the basic methods. I also have the heavy lifting graph methods, like get EagleNet, which is given a center node, get all of its surrounding nodes. Get the strongly connected component. If a graph is not connected, then it will give me, the however number of components that is connected. And I have a depth first search and breadth first search. I have this detect communities, which this is that heavy lifting method that implement the betweenness algorithm. And I have the remote top edge method. And the second class that I use, because you see here the EU, this is counting how many time an edge is used. So this is a helper method class. For this method class, I will just providing it as an input, a path, which path is a array list of nodes, and I supply it a path. Then this method would go to my chart of all the edges and increment the edge that's being used. I've also have a method that would give me the top used edge. So here is the process path method. Here is the top used edge method. And I can also save this chart, which is each of the edge, how many times it has been used, to a file. And I can save the most used edge to a file if I want to. And I can print all of the edges and how many times it's used to the standard output. I can also print what is the top used edge. These will really help you debug your problem. And the third class is called Analyze Network. And this is the main class, where that's the Java main method. And I also have a static method called Get Community, which you supply it a cap graph and how many times you want to cut, how many times you want to loop to remove an edge. That's one time. You loop it again, remove another edge, it's another time. So how many times you want to do this? So this method, the main method, then call this method. And this method, given it how many times I would like to loop, for example, I did for Caltech, I said I want to loop 800 times. So this method will just keep on computing. Okay. So the network data I used, I tried my hands-on two. One is the Amherst College Facebook data, and the other is Caltech. The Facebook data I got is from GitHub. It has about 100 colleges in one day in September 2005. They made a snapshot, and this group of people, and I'm sorry, in my write-up I have this this group's name. I just forget it right now. So I will guide you to my GitHub, where you will find all the documentation and you'll find out where I get the data. So I get all these Facebook snapshot data as a MATLAB format. And I use R, the statistic package, convert the MATLAB format into a text format where my Java code can read. And then I did computation to find out community on both Amherst and Caltech. And because Amherst has 2,000, more than 2,000 nodes and more than 90,000 edges, it took me 2 days to actually just go through the computation once and cut one edge. So I stopped right there because it took too long. And I did then to use Caltech data, which it has 769 nodes and 33,312 edges, so it's significantly less. And for each of the computation, it takes less time. It's probably about 2-3 hours to loop it once. So I set it up to loop 800 times, and it took quite a number of days for me to go through the 800 times. Okay, so here I'm going to switch back to show you the Java program I have. Okay, so I'm going to come here and stop sharing. All right, so now I'm going to share with you my Java code. Hold on just a second and bear with me. And I'm using Eclipse as my tool to write Java code. Okay, so I'm going to share with you my Eclipse. So share. Okay. 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 Yeah, it's starting up. Okay, so this is the social network folder, and this is the source. I have a package for graph, and there is the cap graph. This is the cap graph methods. So we can just really quickly browse through it. I will put all of this code on GitHub, and if you would love to, you can check it out. You can contact me if you see. I'm sure you will see some improvements. So this is the add vertex method, get number of vertices, and the save vertex method, add edge, remove edge, add neighbor, and transpose graph to string, get eaglenet, get strongly connected component, and there is the depth first search, and this is another part, the helper method for the depth first search, and this is to build the strongly connected component, and this is the method to get community, and I will detect the community, and this is where it loops through all the vertices, find the shortest path, and this is the breadth first search, and there's quite amount of code and process path and so on. And this is the helper. This is the helper class where I track how many times a particular edge and all the edges are. So, okay, one thing might be interesting to see is how the data is being captured. So the graph is being captured as a hash map of the node to a set of, so the node is the from point to a set of 2 points. So this is the adjacency vertices structure. And my edge, I use a hash map and I capture the edge as a string, and it's always from node space to node, and to a number of time, the integer number of time is used. And I've also keep a hash set of the most used edges, which is a string with the from node to node, so that I can quickly supply it for those edges to be removed. Okay, so this class is the main class. This is the main method, where how many times I loop. This is the minimum size of graph that I cut. And we can run, I think this is the snowflake example. So we can give that a quick run. Okay, run it. Okay, there we go. So this is where it shows you where the edges are. And this node that connected to 1 or 2, this node connect to a bunch, right? That's the center node that connects to a bunch. And after I identify the top used edge, I cut them, and then I run them again and find the top used edge. I cut them until I end up with a community with just 10 nodes, because I know my community is just 10 size. I don't want to go further, and that's where I sit. So this is how the program does run the code. Well, okay, so I actually like to show you what I found with the Caltech data, which I ran this program for like 10 days. But I'm running out of time, and I will push all of this to GitHub, and my GitHub site is, let me share, let's see. Okay, and let me share screen. I don't know which screen to share, so I'm going to share this one, okay? So I am going to my GitHub. So my GitHub is at github.com/LUAN13242/analyze social network, all spelled out with each of the word, the first one's a capital. So I'm going to push all the code there, and please check it out if you like to. And if you have any comments, send it to me. I am at LUAN1324@gmail.com. Okay, and thank you so very much for watching. I'm going to stop right